Hey, welcome to problem 6 of chapter 7. I like this problem because it does a good little review of kinematics, which, by the way, never disappears, and has a very simple kinetic energy demonstration as well. So, basically, this problem, you should read it in the book. Pause the video and read it before you listen to how I do it. But you got a bead moving, and it's slowing down, comes to a stop at a certain point, then obviously he's going to turn around. It doesn't say that in the problem, but you can think about that yourself. It's going to turn around and speed back up. Anyway, in the very end, it wants a kinetic energy, and concept 1, kinetic energy is 1/2 mv squared. So to get the kinetic energy, we need the speed, and that's going to be a kinematics thing. So what are we given? Well, first off, there's a little picture there, and at first you might think that the picture is not really necessary, but then you realize that you need 5, 10, you need a displacement, which is not stated in the problem, in the words, so you have to get that off the diagram. So yeah, this diagram is a position in meters. Gosh, the resolution of this pen sucks. Sorry, dang. Meters, 0, 5, 10, 15, 20, and at t equals 0, it's here. At t equals 3, it's here at 18, and it also tells you T1 and T2 where it's at, but you don't really need those, just except for the fact that they're 1 second intervals, T equals 1, T equals 2, so you can see that it's basically slowing down. It covers less distance each time. So anyway, we know that V initial is 12 meters per second, and that happens at t equals 0 seconds. V final, it says it comes to a rest, comes to a stop at t equals 3 seconds. That's right here at 18 meters. So the displacement during this time is 18 meters. You have to read that off the little diagram here. What else do we know? That's really all we need. We need to find the acceleration, because there is a constant force acting on the bead, so there is one acceleration for the whole time. Then we need to know the v at 10 seconds, which we're going to use more kinematics. So let's get started. The first kinematics equation, that we'll use. Okay, let's just erase that. Is delta v final squared equals v initial squared plus 2a delta x. I'm not going to do some crazy algebra. I'm just going to plug in the givens here, and then if you want to verify the algebra, you can. This is 0 squared equals 12 squared plus 2a times 18. Solve and you get a equals -4, which makes sense because we're moving in the positive direction, yet slowing down. So acceleration must be going in the must be negative in order to slow down. Meters per second squared. That's the a. Now we can find the velocity at 10 seconds, just using this equation. V final equals v initial plus at. V final equals 12 plus -4 times, now we want the speed at 10 seconds, so we're going to use 10 for t, and you get v final is -28 meters per second, which should make sense because if the acceleration is negative and we start moving this way, we're going to slow down, stop, turn around, speed up, speed up, speed up, speed up, speed up. So we reach a speed of negative 28 meters per second. Now, what's the kinetic energy at 10 seconds? 1/2 mv squared. The mass given in the problem is 1.8 e to the negative 2 kilograms, and the velocity, the square means that the negative doesn't even matter. I'll just stick it in just to be picky, but it doesn't matter because the square will cancel. So that equals 7.056 joules. Yeah, so we had some kinematics review and a basic use of kinetic energy, the energy of motion, the energy with a certain speed. That's it. Alright, next problem coming up.